Welcome viewers to the fourth segment for the fourth lecture for the online series of lectures for the course of Algebraic Topology 1. In this segment, we'll start with the definition of lifting correspondence. Let P, as usual, be a covering map from the covering space E to the base topological space B. Let B0 be a point in the base topological space. Choose the point E0 of the covering space E so that P of E0 is equal to B0 given an element the class of F being in the fundamental group of B with reference to the base point B0. Let F bar be the lifting of F to a path in E that begins at E0. From lemma 1, we know that such an F bar exists and it is unique. Okay, but we never talked about the final point of F bar, right? Now we'll have this final point of F bar coming into play. Okay, let phi of the class of F denote the endpoint F bar of 1 of F bar. Okay, note, since P composed with F bar is equal to F from the property of a lifting, one has P composed with F bar evaluated at 1 is nothing but just F of 1, and we know that since F is a loop based at B0 in the topological space B, F of 1 is the same as F of 0, which is equal to B0, right? B0. So I'm putting a small note here. F of 0 is equal to F of 1 is equal to B0, since F is a loop based at B0 in B. And hence, one follows from here. F bar of 1 belongs to the set inverse image of B0 under P. Okay, so we draw a diagram here. This is the covering map P from the covering space E to the base topological space B, and since F is a path, in particular F is a loop in B based at B0, it's of course a map from 0, 1 to B. Okay, and E0 is a distinguished point in the covering space E such that P of E0 is equal to B0. And we know that there exists a unique lift of F in the covering space E such that the path F bar has the initial point to be E0. Okay. This is the commutative diagram. We therefore have phi to be a well-defined set map, right? A well-defined set map. Okay. Phi from the fundamental group of B with reference to the distinguished point B0 to the inverse image of B0 under P given by phi of the class of F is equal to F bar of 1. Okay, F bar is the unique lift of F that starts at the point E0. Okay, all right. Now we quickly check that this is a well-defined set map. Okay, so this is a set, this is a set, hence phi is a set map. Let me erase everything. We are going to check that it's well defined. Phi defined as phi of the class of F is equal to F bar of 1. Okay. It is well defined since if we choose two elements of the fundamental group that belong to the same class, right? Suppose we choose the class of F to be the same as the class of G, okay, which means that F and G, the two loops, belongs to the same covariance class of the fundamental group. In phi 1 of B with reference to the base point B0, one has, if this is the case, then one of course has phi of the class of F to be equal to phi of the class of G, and hence it's well defined, and they happen to be in the set, in this set, inverse image of B0 under P. Okay, indeed, and why this is so? Indeed, if the loops F and G are path homotopic in B, they are path homotopic since they belong to the same class. Okay, then by theorem 1 earlier in this lecture, their corresponding lifts, their corresponding lifts F bar and G bar in E are also path homotopic, right? From the statement of theorem 1. In particular, F bar and G bar begin at the same point, which is F bar of 0 is equal to G bar of 0, okay? They start at the same point and they also end at the same point. Which is F bar of 1 is equal to G bar of 1. Okay. So the fact F bar of 1 is equal to G bar of 1 amounts to that phi of the class of F is equal to phi of the class of G. Okay. This is what we have here. Okay. In other words, the map that we defined a while ago, which is denoted by phi, is a well-defined set map. Okay. We call phi the lifting correspondence. Derived from the covering map P. Derived from the covering map P. Okay, good. So now we have our second theorem of this lecture. Theorem 2, which states that if P from E to B is a covering map, and if P of E0 is equal to B0, also if E is path connected, then the lifting correspondence phi from pi 1 of B with reference to the base point B0 to the inverse image of B0 under P is surjective. So we want to show that the lifting correspondence is a surjective map in case we have E to be path connected. If E is simply connected, then this map, the lifting correspondence we have here, is bijective. Okay. So this is the statement of theorem 2. Let us prove it. Here goes the proof. If E is path connected, then given E1 in this set in inverse image of B0 under P, which is a subspace of the covering space E, and P of E0 is equal to B0, this is also given, so that E0 is also in this set, right? E0 is also in the inverse image of B0 under P, being a subspace of the covering space E. One must have, since E is path connected, so these 2 points lie in E, so the path joining these 2 points will also be inside E. One must have a path F bar in E from E0 to E1. That is, F bar is a map from 0, 1 to E with the starting point being equal to E0 and the end point of the path being equal to E1. Okay, good. Okay, so then F is equal to P composed with F bar, right? Now I'm claiming that F which is P composed F bar is a loop in B based at B0 in B. This is the claim. Let's check it very quickly. Indeed, F of 0 is equal to P of F bar of 0, which is P of E0, right? Since F bar of 0 is E0. And P of E0 is, by hypothesis, equal to B0. Also, F of 1 is equal to P of F bar of 1, which from this can be written as P of E1 and P of E1 is equal to B0. Why? since E1 is in the set which is the inverse image of B0 under P. So the initial and final point of F lie at B0, which is a point of the base topological space B. Okay. Now, which means that the class of F is in the fundamental group of B with reference to the distinguished point B0 with F bar of 1 being equal to E1. Okay. Which is of course an element of this set, inverse image of B0 under P. Okay. Therefore, by the definition of lifting correspondence, phi of this class of F is equal to E1, the final point of the lift F bar. In other words, we just have shown that for a given E1 in the set P inverse of B0, which is the inverse image of B0 under P, there exists a loop F in B based at B0 with phi of the class of F is equal to E1. We just have shown it. It means that phi is surjective. Okay. So we just have shown that if the covering space E is path connected, then the lifting correspondence phi is a surjective map. Okay. Now let us prove the second part of the theorem. Now suppose E is simply connected. Let the class of F and the class of G be two elements of the fundamental group of B with reference to the distinguished point B0. With phi of the class of F to be equal to phi of the class of G. I need to show that the class of F is the same as the class of G. To prove that phi is injective, right? So F and G are loops in B based at B0. Also, we are given that P of E0 is equal to P0. Let F bar be the unique lift in E starting at E0 in E, right? The existence is proved in lemma 1. Okay, so we denote that unique lift by F bar. Okay, also let G bar be the unique lift of G in E starting at the point E0 of the covering space E, the existence of which is also guaranteed by lemma 1. Okay, okay, in other words, both of F bar of 0 and G bar of 0 are the same and are equal to E0. Okay, this is our equation number 12. Now we are given this fact, right? Now we are given that phi of the class of F is the same as phi of the class of G, which means, according to the definition of lifting correspondence, F bar of 1 is equal to G bar of 1, right? Which we define as E1 bar, okay? Therefore, F bar and G bar are two paths in E between E0 and E1 bar, okay? So this is our topological space E. So F bar and G bar are two paths which start at the same point E0 and ends at the point E1, okay? Okay, good. Now by lemma 3 of lecture 2, okay, then F bar and G bar are path homotopy, since this topological discovering space E is simply connected. Okay. So in other words, intuitively speaking, so there is no such hole here. Okay, so that you will always be able to continuously deform S bar into G bar. Okay, there is no such hole here. Okay, so get back to lemma 3 of lecture 2. It will be clear that F bar and G bar will be path homotopic since the underlying space is simply connected. Okay, so we just have seen that F bar and G bar are path homotopic in the covering space E. So now, using the second key fact used to prove theorem 1, then by the second, so we had two key facts that were used to prove theorem 1 of lecture 1. So by the second key fact, used to prove theorem 1 of lecture 1, P composed with F. Okay. Is a path homotopy okay. So we are also, so these two guys are path homotopic in E. Let F bar be a path homotopy between F bar and G bar in E. Okay, since they are path homotopic, I can always find a path homotopy between them. So we are denoting a path homotopy between them by F bar. Okay. So by the second key fact used to prove theorem 1 of lecture 1, P composed with F bar. I think it should be bar. Has to be corrected on the note. Has to be bar. Alright, so there is a correction in the lecture note. So P composed with F bar is a path homotopy between the paths P composed with F bar and P composed with G bar in the base topological space B. Okay. In other words, so remember that F bar was the unique lift of F and G bar was the unique lift of G. Okay, so that P composed with F bar is equal to F, and P composed with G bar is equal to G. Okay, so in other words, here F and G are path homotopic in the topological space B. That is, these two paths, F and G, which were taken to be loops based at B0 in the topological space B, belong to the same class. Okay, so so we started with the fact that phi of the class of F is the same as phi of the class of G, and we ended up proving that the class of F is the same as the class of G. Okay, which means that phi is injective. Okay, and it's given that E is simply connected, which means that E is also path connected, right? And by the first result of the current theorem, phi then is surjective as well. Hence, phi is bijective. So, in case we have the covering space to be simply connected, we then have the lifting correspondence to be a bijective QED. Okay, good. Now the main theorem of this lecture. So we have been doing all these things. So we are preparing to prove this theorem. We developed all these tools. We defined the lifting correspondence to prove this main theorem of the current lecture. Now, the main theorem of this lecture. Main theorem of this lecture. Theorem 3. Let me state it first. The statement is pretty simple. The fundamental group of the unit circle S1 is isomorphic to the additive group of integers okay. It needs to be proved. Let us prove it. The main theorem. Let we choose the familiar covering map P from the set of real numbers to the unit circle. Okay, so this is the covering map. Introduced in lecture 3. Lecture 3. The map P is defined as P of x is equal to cosine 2 pi x, comma, sine 2 pi x. This is how we define this covering map. In lecture 3, we have proved that it's indeed a covering map. Let also E0 is equal to 0, which is the origin of the real line. Okay, that's the point E0 in this case, and the base point here is taken to be the point 1, 0 on the circle, which is P of E0. Okay, or in other words, P of 0. So if we plug in 0 here, we get 1, 0, right? So that B0 is equal to 1, 0. That is a point on the unit circle, right? The circle is thought of as a subspace of the Euclidean space R3. Okay, so we have seen earlier in lecture 3 that the inverse image of this point 1, 0, which we have denoted by B0, is the set of integers. Okay, so yeah, it's evident from here. Now you choose x to be an integer and you will always get 1, 0. Okay, good. Now note that now this guy R, the covering space R is simply connected, right? R is simply connected. So by theorem 2, the last theorem, the lifting correspondence phi from the fundamental group of the circle S1 with reference to this base point B0 to the group of integers, to the set of integers, which is of course the inverse image of that point B0, is bijective, right? Since this is this covering space is simply connected, right? So it follows from theorem 2, the last theorem of the ongoing lecture, that this lifting correspondence is bijective. Okay, good. We have gotten this far. We now have to show that, this map phi is a homomorphism. Just have to show that it's a group homomorphism. Then we are done proving that it's an isomorphism of groups. Okay, good. So let me erase everything. So the goal now is to show that this lifting correspondence of the fundamental group of circle with reference to that distinguished point B0, where our B0 is 1, 0, on the unit circle, to the set of integers is a homomorphism of groups. This is what we want to show. Okay, so given two elements, the class of F and class of G, in the fundamental group of the circle with reference to this distinguished point B0, let F bar and G bar be their respective liftings to paths on the real line beginning at E0, which we chose to be the origin of the real line. The existence and uniqueness of such a lifting guaranteed by lemma 1, right? That is F bar of 0 is equal to 0 is equal to G bar of 0. So both these lifts start at the point 0 of the real line. Okay, so let me draw a diagram for this situation. We have the covering map from the set of real numbers, the unit circle, which is P, right? And we have two loops, F and G, on this circle S1, which are just maps from 0, 1 to S1, and we denote the unique limbs of these two loops in R, which are F bar and G bar respectively. Okay, and so there is this point B0, and there is this point 0 in the real line, such that P of 0 is equal to B0. P of E0 is equal to B0, where our B0 is 1, 0. Okay, this is the commutative diagram. Okay, good. Now let n equal to F bar of n. So now that we have these two unique lifts, we take the final points of these lifts. Okay, and the final point of F bar is taken to be n, which is an integer. We will see shortly why this is an integer. And m, we choose G bar of 1 to be n. Okay, in fact, let us see why. In fact, P of F bar of 1 from the property of lifting is equal to F upon, okay? And F is a loop in the unit circle that starts and ends at the same point B0. Okay. And the same is true for P of G bar of 1, which is G of 1. G is also a loop based at 1, 0 in S1. Okay. And this is the case since F and G are both loops based at B0. Okay. so that both f bar of 1 and g bar of 1 belong to the inverse image of B0. Okay, it's clear from this and this. And inverse image of 1, 0 under this covering map P is the set of integers, right? So f bar of 1 is taken to be n and g bar of 1 is taken to be m, two integers. Okay, alright, so we have chosen n to be equal to f bar of 1 and we have chosen m to be equal to g bar of 1. Okay, so in other words, from the definition of lifting correspondence, phi of the class of f is equal to n and phi of the class of g is equal to n. Okay, now let G double bar be the path in the real line, that is from the definition of path, G double bar is a map from 0, 1 to the set of real numbers defined by, so I'm defining G double bar. G double bar of S is equal to n plus G bar of S. This is our equation number 14. Okay. Now since our covering map P from the set of real numbers to the unit circle is given by P of x is equal to cosine 2 pi x sine 2 pi x. From the property of trig functions, one immediately finds that P of n plus x is equal to P of x. So just replace x with n plus x, you get back to the same expression, cosine 2 pi x sine 2 pi x. So one has P of n plus x to be equal to P of x for all x in the set of real numbers. This is our equation number 15. Okay, and 14 and 15 together imply that P composed with G double bar of S is P of G double bar of S, and from the very, so I just replace G bar of S with n plus G bar S, which is P of n plus G bar of S. Now using this property, it is nothing but P of G bar of S, and since G bar is the unique lifting of G, this is just G of S. Okay. so that one obtains P composed with G double bar is just G. So this equation 16 implies that G bar is a lifting of G. Okay, good. Now also note that G, so we have this expression of G double bar, right? G double bar, so we defined G double bar of S as N plus G bar of S, right? Which was equation number 14. So we just plug in S to be 0 here, and we see that G double bar of 0 is equal to N plus G bar of 0. Okay. And F bar and G bar, they were unique lifts, right? Starting at the point 0 of the real line. So this guy is 0. So that this is just N. Okay. Now here is the thing. G double bar, although G double bar is the lift of G in the real line R, it does not start at the point 0. It starts at a different point N. So there is only one lift of G that starts at the point 0 of the real line, namely G bar. So although we are finding another lift, G double bar of the same loop G, it's not violating the statement of lemma 1, since the starting point of this second loop G double bar is a different point with N, which is different from 0. Okay, good. So we just found a lifting of G that starts at the point N of the set of real numbers. Okay, so let me write it. Therefore, G double bar, which is a map from 0, 1 to the set of real numbers, is the lifting of the map G, or the loop in the unit circle S1. And since it's a loop, the initial point and final point are the same, and that common point is B0 of the circle, of the unit circle. Okay, let me erase this bottom part. Good. So and also this guy begins or starts at N in the set of real numbers, which is an integer. Also, N is equal to F bar of N. Okay, we chose F bar of N to be N, remember? That is F bar ends at n, where F bar is a map from 0, 1 to R as well. Okay. Therefore, one can form the product concatenation of path. One can form the product given by F bar star G double bar. Okay, so G double bar starts at n. Okay, and F bar ends at n. Therefore, we can form this product. This is well defined. Okay, so one is allowed to form this product. Now the claim is that F bar star G double bar is the lifting of the loop. One can always form the product of these two loops in the fundamental group of B with reference to the distinguished point B0, right? So now the claim is that this guy is the lifting of the loop F star G that begins at 0 of the real line. Okay, so in the rest of the lecture we'll prove this claim. Okay, now again we are going to use the second key fact of the second key fact during the proof of theorem 1 of lecture 1. Use the second key fact to prove theorem 1 of lecture 1. Okay. One immediately finds after applying that second key fact that P composed with F bar star G double bar to be equal to P composed with F bar product P composed with G double bar. Okay, and so since F bar is the lift of F, we have P composed with F bar to be equal to F, and since G double bar is a lift of G, P composed with G double bar is going to be equal to G. Also, F bar star G double bar begins where F bar begins. Okay, we know from the concept of concatenation of paths that the starting point of this guy is the starting point of the first path, right? And the ending point of this concatenated path is the end point of the later path. This latter path is G double bar. So the ending point of this path is going to be the ending point of this concatenated path. Okay, so F bar. So this is the where does F bar begins? Where does F bar begin? That is at F bar of 0. Okay, and we know that F bar of 0 is 0, right? So both F bar and G bar begins at 0. Is at F bar is equal to 0 is which we denoted by E0, right? Okay. Now, since F star G is a loop based at B0 in the base topological space B, and P of E0 is equal to B0, in view of our equation, this is our equation number 17, in view of the equation 17, F bar star G double bar is the unique lifting starting at E0 is equal to 0. Okay, so the endpoint of G double bar, the endpoint of this lifting F bar star G double bar is the endpoint, as we have discussed earlier, of G double bar. Okay, that is G double bar of 1. Good. I need some space to conclude the proof of this theorem, the main theorem. Okay, with F bar star G double bar, this guy evaluated at 1, we are evaluating the endpoint of this concatenated path, and which is supposed to be equal to the endpoint of the latter path, G double bar of 1, which according to the definition of G double bar is equal to n plus G bar of 1, and we chose G bar of 1 to be equal to m, recall. So this is n plus m. This is our equation number 18. Okay. Then, using the definition, the very definition of lifting correspondence, phi of the class of f star the class of g. We are taking the product of these two loops in the fundamental group of B with reference to the distinguished point B0, and so from the well-definedness of this product, we know that this is nothing but the class of the product of the two loops f and g, and using this definition of lifting correspondence, this is nothing but, the lift of this is, which is f bar star g double bar evaluated at 1, the final point of the lift. And we have seen that this is equal to n plus m in equation number 18, right? And phi of the class of f plus phi of the class of g is equal to f bar of 1 plus g bar of 1, which according to our assumption is n plus m, right? So that one immediately has phi of the class of f star the class of g is equal to phi of the class of f plus phi of the class of g, which proves that phi is indeed a group homomorphism between the group of the fundamental group of B with reference to this distinguished point B0 to the group of the additive group of integers. Okay, QED. This is the end of the fourth lecture. Okay, so this was the goal of the fourth lecture. We wanted to compute this first non-trivial fundamental group, that is the fundamental group of the unit circle. We have shown that this fundamental group of unit circle with reference to a certain base point is isomorphic to the additive group of integers. Okay, next lecture we'll be studying retraction and fixed points. Okay. Thank you for attending the fourth lecture.